Yeah, let's get started. Although it's almost impossible to get started after that delicious lunch, but I will try my best here. So I'm Stepan, a worker in Provectus and Hydrosphere.io. The title today is Monitoring AI with AI. There are two AI buzzwords in the title, but I promise you to share very practical things and hardcore stuff today. So before I start, I want to give credits to our amazing team, and of course this talk is based on our joint research, joint project. So for some slides I probably not hands-on as much as I would. So let's move ahead. So to warm you up, let's recall that comparison table between traditional software and machine learning applications. So this is like baseline that everybody of you should definitely know. But from the Wikipedia, of course, traditional software is a set of explicit business rules, what we define our domain here. Versus machine learning is driven by machine learning generated model that describes our world. Traditional software is tested with unit tests. It's covered by unit tests, and some kind of similar approach and concept is model evaluation in the machine learning world. The software is being delivered as services, or nowadays microservices, and basically similarly machine learning applications tend to be delivered as a service. You can recall Google services, Amazon services for image recognition, for text services, and other stuff. Physically, software is being deployed in Docker per server, and the same way most often machine learning applications are being deployed with Docker per model. Those were similarities. Now let's discuss some differences. So usually in traditional software world, we have one microservices in one version of microservice in production at the same time, versus machine learning, when we might have 1, 10, 20 different versions of the same machine learning model in production, consuming traffic and making a prediction. Usually, one software engineer and one software engineering team and one QA team owns a traditional software project, when one machine learning engineer can own multiple projects, multiple machine learning models at the same time. So you can feel the scale. Now, in traditional software, it fails loudly. We have exception, we have stack trace, we can catch it, and we know how to operate it. Versus machine learning applications, they fail silently. So we still get predictions, but there is no exceptions in our physical exceptions that those predictions are wrong, and we need additional tooling around to catch those exceptions and catch those inconsistency. And if we have a proper process, if we have unit tested, we have manually tested, some software can work forever, almost forever, versus machine learning, when we really expect from the day one that our production behavior will be different from laboratory, from research. So performance declines over time, and I want to warm you up from some public use cases, and you can see what is the cost of AI error in production. Yeah. So let's start with some funny examples. It's well-known research about adversarial networks and adversarial attacks. Probably, just to remind you, we have an original image, we have some attacking noise, and our model recognizes toaster instead of sports car. It recognizes Keanu Reeves instead of Sylvester Stallone. So that's funny, but let's check the next example. So it's already not funny. Also publicly well-known use case. It may cost companies reputation. It may cost your marketing and PR department to fight with and mitigate that impact from these AI errors here. And just step back. And the point I want to highlight here that even Google, at Google scale, at Google skills, and decades of experience running production systems, they could not solidify on 100% their production machine learning models here. Then another publicly well-known use case with TieBot from Microsoft. If you remember, they launched that TieBot and it became a racist after 24 hours of after launch. And also the question is, was it possible for Microsoft to test it before and monitor it right in production and adjust its behavior and prevent that unexpected shutdown of AI? That was a research experiment, but this is like a public lesson for society that it might be dangerous here. Another domain, Coinbase, fraud detection system had failed, and yeah, it basically cost us money here. Another use case, when the fraud detection system has been, I guess it was properly tested in some data sets, and once deployed to production, it made that company even shut down their business after that unexpected launch here. And the question to audience, you guys, what do you think, where and why may AI fail in prod? Just your thoughts, just speaking aloud. Okay, actually it's everywhere, it's obvious, it's a software, it's pretty complicated stuff, yeah. A lot of moving parts, especially in that pipelines, our data pipelines, and so on. So there are like infinity list of reasons and root causes why it may fail. It's bad training data, bad serving data, training serving data skew, some misconfigurations and deployment issues, and you can name it. And of course, there is no one silver bullet how to make it reliable. I would like to cover some aspect and structurize a little bit like further talk, and then we will focus on like on a cherry on a cake with that. So, in order to structurize my talk, let's like take a look at that AI reliability pyramid, and the basics is training and serving pipeline infrastructure. So without that, you should not go to production, or it's obvious, yeah. Then the deployment infrastructure, the model management infrastructure, and then monitoring of your data, monitoring of your predictions, and the cherry on the cake is handling that concept drift, handling that drifts of your model and the degrades of performance of your model. So I will cover very briefly that two basic things and then move to the main topic of this talk. So this is an example of like reliable training serving pipeline. Of course, we should eliminate data silos, and data scientists should experiment right with production data. It might not be like exact production data. It should be fresh, up-to-date, diverse, and clean data sets that are, in this case, it's like a Kafka-based pipelines, and we can easily create such a comfort zone for data scientists in the middle of production. So you can iterate right there and deploy the models to the main pipeline. So we can use a concept like shadowing and mirroring the traffic and creating such a loop here. So it by design, it eliminates half of the reasons I listed the 2 slides before. So, what do I mean by model deployment infrastructure? So, how can we actually take that black box, where the artifact after the machine learning training pipeline, it might be pickle file, it might be zip file, parquet file, protobuf, whatever, and integrate it into the application. So, very briefly, we have a lot of stuff here, like model server, gRPC server, some cluster-based, cluster-aware things like sidecar that handles the logistics and plumbing of this stuff in production. But the most important thing is that we need to have a training data statistics packaged into the model deliverable in order to provide a traceability and auditability and monitoring for any model we put in production here. And the next thing, as we deploy something to production, we need to monitor it. Yep. Basically, there are 2 questions to be answered in that stage. Is the model degraded? And if yes, what is the reason here? Let's start with the most simple thing that may happen in your data pipeline. So today you might have your features, a feature vector that accepts doubles, numbers, whatever. And for example, the age feature might be drifted towards year silently because data engineer started doing something wrong. And actually, like physically, your model will accept those numbers because it's still number. So you should like be aware about that. The numbers might be changed to strings. The categorical features might be changed from one range to another range. So the basic thing how to solidify this is to use schemas. It's protobuf schemas, Avro schemas. So every stage of your pipelines should be described in like schemas, and it will eliminate data format issues between your stages. But that's fine. But let's move further. What else might happen in production? It's a so-called concept drift. So you trained your model on a original concept, and in this case, it's just like a simple classifier that classifies one thing from another. And in production, you might have something different. It's a drifted concept or new or emerged concept here. I guess visually, it's like intuitively, it's pretty clear what may go wrong here. So, and let's start like designing that system together. So, when like data scientist builds the model, trains the model, it makes some assumptions about the properties and features of the data he works with. And when we push it to production, the model works if and only if the statistical properties of your training data are the same as in production. It's pretty obvious and I guess clear for everybody. And so as a result, we need to continuously explore data in production or continuously build a data profile in production and compare it with the data sets that we used to train our model. So we can, from simple statistical stuff like mean, max, mean, data skewness, and range, and all that stuff can be like encoded into a protocol of our model that our model exposes to the outside world. So in this way, we can basically automatically create such a rules. If our age is more than 100, then it's abnormal behavior. Yeah, we can send a metric to our like a monitoring system. Okay, we have a lot of out of range features for a particular model. Yeah, this may work, but it looks like a small unit test for every feature we have, and this is very time consuming, and doing that manually, it's almost impossible to. If you have like 200 features, you have to describe all the like 10 statistical properties of every feature, and this is impossible. So of course we should automate it, and we generate such a small checks, small metrics out of our features automatically. There are well-known like data profiling techniques. So when you take the data set and you just profile it. So yeah, as I mentioned, that every metric will every feature will generate dozens of small metrics to be monitored. So if you have hundreds of features, it will generate a couple of thousands metrics to watch. So there are some statistical metrics that is worth to explore. It's Kolmogorov-Smirnov test. Basically, it tests if two distributions if two samples are from the same distribution. It may help. Some quantile plots, simple correlations, and density-based algorithms. It works well for like one-dimensional data sets and for tracking one particular feature from the vector. But how to deal with multi-dimensional data sets, how to deal with image data, test data, how to deal with like complicated seasonality that could not be described as a set of simple rules in our protocol. Here, let's remember that guy who said once upon a time that you should send a maniac to catch a maniac, and let's do the same. And our like evaluation of our approach is the same as in like evaluation of machine learning methods. Before, like 10 years ago, there were rule-based programs. Then we switched to like statistical models. Then we switched to machine learning models, and now to deep learning models. Yeah, the same way we started with like solidifying our pipeline by defining some rules, explicit rules. Then we used like statistical methods for like Kolmogorov-Smirnov to test it, and now let's explore more sophisticated stuff for anomaly detection, for detection of concept drifts. Yeah, those one. Some of them I would list it. What we use, so it's ongoing research. We're trying different methods, different stuff. Something works, something not. But at the end of the day, we stack them all together, and like as an ensemble, they provide a very good insights what's happening in production with your data. So deep autoencoders, you can treat it as a snapshot, of statistical properties of your data. So you can train autoencoder on your training data, and then use it to reconstruct production data if the error is like higher a threshold than a threshold. You can treat it as an anomaly, yeah. But of course, it's not like a self-explainable feature, not self-explainable method. Generative adversarial networks. I guess the like a canonical use case for GANs is detecting adversarial attacks. You probably follow that research. This is amazing. How we use that is to detect not an adversarial input. We use it to detect a drift in concepts. I will explain it in a second. Then MADE, masked autoencoder density estimator. That's another like a recent papers, recent research. I will explain how it works in a second. Random cut forest. Actually, there is no open source implementation of this algorithm. It's actually a robust random cut forest. This is a paper published by Amazon Kinesis. They use that algorithm for anomaly detection in Kinesis streams. We basically took that paper and implemented our own version of that algorithm. We tested out, and it works pretty well. Especially like on a streaming data when we have to detect anomalies in real time in a particular window here. And of course, you can apply model-specific versions when you know those methods are kind of model agnostic. At the end of the day, you have doubles, vectors, and you can watch them. If you know your model specifics, you can apply your own your model-specific metrics here. So GANs, how it works. Basically, the screenshot from the original research. The idea is like dumb simple here. We can train discriminator to detect drift versus normal data that we are aware of. So in original case, they detected fake data, fake images versus original images. We detect good data versus drifted data here. Masked autoencoder. So these are basically autoencoders. This is actually not. This is not an autoencoder. It might be misleading from its name. It's a neural network with some dropped connections that is trained by additional masks. And at the end of the day, it can provide a method for estimating a density of your input features. So, and we can use that model to guess, for example, to guess that particular image belongs to the distribution we knew before. You can think about that as you. It's like a Kolmogorov-Smirnov test on a multi-dimensional context. In this case, we trained our MADE model on MNIST data set, and then we feed it with cat image, and yeah, it actually says probability of belonging to learned distribution is like almost 0. This is a binary data set, black and in original paper is also a binary data set. There are other like ongoing research how to make it in grayscale, and we actually use that concept to detect, for example, that car, I don't know, is on a snowy road instead of the car is being drove by Palo Alto campus, for example. Yep. Yeah, and at the end of the day, all these methods provide some metrics, counts, and like histograms to monitor. And this is like a 2D plots that we can use to detect particular anomalies and make alerts out of that. So it could be operationalized and could be used for like a usual traditional workflow for monitoring a software. Another like use case for text, classical models for NLU is encoder decoder. In this case, it's encoder labeler, and we can monitor intermediate representation of this, and also detect some drifts or detect new concepts out of that. And in this research, we basically trained the model on restaurants data and then fed that model with some random Wikipedia data set. So, and is, what is? Yeah, so you can see here that like cluster of bad data, you can distinguish cluster of bad data from cluster yellow and blue of like development and test data here. So once we like recognize that something is not good in with our production traffic, what can we do about that? So the last like cherry on the cake, how to handle that? You can send just an alert, you can do something else, and basically the main idea of automating the production is to enable an automatic retraining of the models. Yep, and actually, if we detected the drift, it might be expected and unexpected. Expected drift is that's something we know in advance that the behavior of our user will change over time, yeah, and our features will be drifted a little bit. We expect to retrain our model with the latest data sets. Or if we have like unexpected drift, is something that happened, of course, unexpectedly because of some upstream failure, for example, and our model is being fed with just incorrect features. So in this case, of course, we should not retrain our model because it will like the errors will propagate from the training to the serving pipeline, and you will be like have hard time cherry picking that like bad features later. So, and this is actually also an interesting open question, how to classify that expected versus unexpected drift, and we can use machine learning for doing that as well. And this is a diagram of just a process diagram, yeah. So for retraining, the first question is when to retrain, then what data to use for retraining, and basic naive approach is to manually watch every single model and then manually subsample data from production, manually retraining. Of course, it works pretty well, but it doesn't scale. There is another naive approach, just to automatically retrain with the latest data batch. It's also like error prone because it's not safe. It can be expensive. If it's required manual labeling of your data, you could not label just the latest batch and retrain with that. You can appear in a local minimum or maximum, so you need a latest batch doesn't mean the best data you have. The latest batch at the end of the day, you need a diverse data set from latest batch, from the history, from to catch all the patterns here there. And what we do and what we propose is there's no like coined. The name of that is not coined yet. It's basically an automation of that stuff using algorithms for monitoring. So we profile features in production. When we detect a performance degrade, we generate, as far as we know, all the statistical properties of our data. We can generate diverse and clean data, retraining data sets. If it's like a supervised use case, and if it's required external labeling, we can send that minimally required data sets for relabeling. That's actually also a big deal. You can't send like everything to relabeling because you might send like hundreds of similar images, and it will be just a wasting of your money and wasting of your time. So once relabeled, we can use that retraining data set for the later automation. So then it's just a matter of automation to complete that loop in production. That's basically it. I'm happy to take questions. No. Oh, yeah. There.
Couldn't see you. Hi there. So I've got a couple of well, I've got many, but we can take it later. Yeah, we talked yesterday, but I've got a couple of questions. The first one is, do you guys have the, in terms of testing the quality of the data, do you have the GANs method in production? Because I'll explain you why. Because first of all, my experience with GANs is they're really, really hard to train. They have a convergence problem. It takes ages. So when a GAN might tell you that this is fake data, that is not real, it might be because it is fake data, or it is not as much quality as the input, but doesn't necessarily mean that it is not good data. And the second one is it might also be part of the training, that the training, the lack of proper convergence, because the loss functions don't mean much in some GANs. So do you guys have it in production?
So GANs, actually it's in production we usually use like a stack of different methods. So you can use GANs on top of other methods. So if they trigger all together, it's like a double sign of that something is going wrong. So we can like smoothly deploy new methods and test them because we can analyze the same traffic with the different models at the same time. And if our like statistical methods don't work, sometimes our like more sophisticated deep learning methods work. And vice versa. With GANs, yes, of course there are some tricks to make it work. Actually, it's probably like a subject for a separate presentation of the whole paper, how to use GANs for anomaly detection, how to use GANs for concept drift detection.
Okay, and the second question is, I'm actually highly interested. You saw a slide with a non-risk environment for data scientists, and that is like my dream come true. So how does this environment look to you? So at the moment, as we were talking yesterday, we are trying to build this environment in my company. We're trying to replicate the least amount of data possible, which means building some bridges between development and live environments. Yep. So how you go about it? What is your experience?
So in that particular case, it's Kafka-based, the data streams, data pipelines, and we basically serve the data that flows through the Kafka stages, and if it's and also we shadow that data. So basically, it's like a serving first architecture. When you don't start with training pipeline, you start with serving pipeline. And your training pipeline is just a fork of your training. It's just an offline fork. That's the main idea. And it might be like, in this case, it's a Kafka-based. It might be just a plain gRPC-based flow. It doesn't matter.
So how you make sure your data scientists don't mess with the live environment? How you make sure they don't, for example, switch off the service, for example?
How do we make sure that data scientists do not
mess with the live environment?
With the probe, there is no silver bullet. Of course, it's architecture. Some things are like eliminated by design. If you what do you expect from data scientists to deliver? It's just your deployable model. I showed you. Let me. I didn't cover much during this talk because it's like a different topic, but If you expect data scientists to deliver such kind of thing, not a delivery, it delivers just a model, an artifact. And then you have the whole process, automated process, of course, to package this artifact, to extract the metadata, to package the training statistics into that, to run it like a testing pipeline before you deploy to production. Then, yeah, it works. So from data scientists, you don't need to know anything about Kafka, for example. You don't need to know anything about like gRPC, whatever you have, you see here. You don't need to know anything about API and clusters and that stuff like sidecar. So it's like it's combined on the fly, right? You deliver just a model, just a like protobuf file from your TensorFlow pipeline, and that's it.